Grab your boots and binoculars because today we're acting as your survival guide to spotting mathematical equations out in their natural habitat. If you've ever stared at a math test and felt like the equations were written in some sort of alien language, well, you're definitely in the right place. In this explainer, we're going to decode that language together.
So, let's dive right into this question. Exam environments are super high pressure, and they can easily make questions feel like a massive, intimidating jumble of numbers and letters. But what our source material reveals is that math at this level is actually incredibly visual. The real secret isn't just crunching numbers, it's learning how to actually see the shapes hiding inside the algebra.
To get there, here's our agenda. First, we'll meet the graph families. Then, we'll explore the core visual shapes, tackle asymptotes, master the rules of transformation, and finish up with your exam survival checklist. Let's move.
Section 1. Meet the graph families.
Okay, the absolute crucial point here is that you aren't actually meant to memorize an infinite number of random disconnected equations. Not at all. You're really just learning a few core families that share common DNA. Once you know what the parent of the family looks like, you immediately know the basic shape of every single offspring in that family, no matter how complicated the specific equation tries to look.
And that brilliantly illustrates our ultimate three-step survival rule for navigating any graph problem you might encounter. Step 1. You look at the equation and recognize the parent graph. Step 2. You identify its inherent default features. And Step 3. You look at the extra numbers in the equation to apply the transformations. That's your core strategy right there.
Section 2. The core visual shapes. Let's contrast two of the most fundamental species. First up is the straight shooter, the linear graph, represented by y equals mx plus c. It forms a perfectly straight line driven entirely by its gradient and y-intercept. Now, completely distinct from that is the quadratic parent function, y equals x squared. It forms a U-shaped parabola, boasting a definite turning point and a perfect axis of symmetry right down its center.
Now, what's really fascinating is how a single sign change in the linear gradient instantly dictates the physical direction of the line. If that m value is positive, your straight line is marching upwards from left to right. But the literal second that m becomes negative, the graph falls. It's an instant visual cue baked right into the equation.
And just like with those lines, simply checking whether the a value in our quadratic family is positive or negative instantly tells you the orientation of your parabola. If a is greater than 0, the U-shape opens upward, kind of like a cup ready to catch water. If a is negative, it flips and opens downward. Again, the algebra is literally drawing the picture for you. Beyond lines and parabolas, we also have the cubic graph, y equals x cubed. This one introduces a really distinctive S-shaped curve that slithers right through the origin at 0, 0. It's got this fascinating odd symmetry right around that origin point. While the parent graph is a smooth S-curve, keep in mind that once we start transforming it, it can definitely develop distinct turning points.
Rounding out our core shapes is the absolute value graph, y equals the absolute value of x. This one is instantly recognizable. It abandons curves completely for a sharp, rigid V shape with a very clear vertex right at the origin. If you see those straight vertical lines framing an x in the equation, your brain should immediately flash a giant V.
Section 3. Asymptotes, reciprocals, and exponentials. All right, it's time to meet the wild cards of the math world, the ones that behave just a little bit differently. But before we look at these specific wildcard graphs, we absolutely have to define their defining boundary, the asymptote. Think of an asymptote like an invisible electric fence. It's a boundary line that the graph eternally reaches for, getting closer and closer as the values stretch toward infinity, but it fundamentally never ever crosses or touches it.
The first graph defined by these invisible fences is the reciprocal graph, y equals a over x. Because you can't divide by 0, the graph mathematically breaks apart. It literally splits into two separate branches divided by asymptotes at x equals 0 and y equals 0. And just like we saw earlier, the sign of a controls everything. A positive a puts the branches in opposite corners, quadrants 1 and 3. A negative a flips them to quadrants 2 and 4.
Similarly, exponential graphs are completely ruled by their a value. This is the graph of extremes. If your a value is greater than 1, you get explosive exponential growth, just shooting upward into the sky. But if a is a fraction between 0 and 1, you witness sudden exponential decay, dropping rapidly before it levels out. Now, no matter how fast it grows or how steeply it decays, the parent exponential graph has some non-negotiable rules.
It's permanently locked in by a horizontal asymptote at y equals 0. That means the parent graph absolutely never crosses the x-axis. And, beautifully, its y-intercept is always anchored steadily at the coordinates 0, 1.
Section 4. The rules of transformation.
Now that we know all the major families and their specific habitats, we need to understand the art of their movement. How do we shift these shapes around the coordinate plane? Well, let's slow down for a second, because this single memory trick is your ultimate survival tool for transformations. If you only remember one thing about moving graphs, let it be this. Changes happening on the outside of the function behave exactly as you'd normally expect. But changes happening on the inside of the function behave exactly the opposite to what your intuition tells you. Let's see this in action.
Applying our trick to algebraic rules, you can see it perfectly. A plus k outside the function shifts the graph up, and a minus k shifts it down, completely normal. But a minus h inside the brackets actually moves the graph to the right, to the positive side. It's opposite. Furthermore, a multiplier a greater than 1 stretches the graph vertically, while a fraction compresses it, and a negative sign inside the function, that reflects the whole thing right across the y-axis.
Section 5. Exam Survival Checklist.
This quick recognition guide is basically your ultimate cheat sheet. Seriously, you should freeze this frame in your mind. It ensures that the very second you see a variable format like an x squared, a 1 over x, or an absolute value bracket, your brain instantly loads the correct visual species. You aren't even doing math yet, you're just identifying the animal sitting right in front of you.
And finally, before your pencil even touches the paper to sketch, run through this diagnostic checklist. Mentally ask yourself, what's the parent shape? Has our outside is normal, inside is opposite rule translated it? Where's the vertex now? Did the asymptotes move? By answering these questions sequentially, you ensure you understand exactly how the parent shape has evolved before you draw a single line.
By shifting your perspective from just staring at abstract numbers to actually recognizing these distinct visual families, you've unlocked a whole new, much more powerful way to conquer your math exams. You are no longer just calculating, you're observing, categorizing, and predicting. So the next time you face a massive equation, I have to ask, are you going to let the numbers intimidate you, or will you look closely enough to recognize a familiar face?